be E or capital E, both. All right. What happened? Okay. So exponent can be defined with an E or capital E. What we can do is we can get rid of this E and capital E's and make sure that we have all the lower cases. Okay. Okay. Mm, we just have to return a true or a false if it's a number or not. Okay. So whenever we have string parsing like this, the way of solving this is by using something called as finite state machines. Finite state machine is basically going to say you start from some state and then you move to next state. Okay. And then you move to next state. So that is what will happen here. So you start from one state, you know what is your starting state. This is defined. From this state, you can go to maybe one or two other states, and from that state, you can go to multiple states. So what we can do is we can start thinking about this finite state machine. We know that our start uh, has to be, let's think. So, and have all of these numbers here, right? So our start has to be either a plus minus sign. Okay. So our start has to be one of this. So it has to be either a plus, a minus. Okay. Our start has to be plus, a minus, or anything from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So one of this is going to be your start. Okay. Let's think. So you have a starting. So we know that our start is starting from there. The state that comes after start. Okay. That means, let's say you have seen, let's say a number or an this. Okay. So the start is also going to have two optional things, which is start with sign. Okay. Which is going to only have this, and then you need uh, this is optional, right? So it can be, yeah, it can basically be one of this, or you start with the numbers. Okay, these are your numbers, right? So one of this is your number. These are your valid numbers. These are your valid signs. Okay, let's just create valid alphabets, which are only E or capital E. Okay, and then what else you have? Um, Character by character, right? Okay. Um, all right. So we can start parsing this particular thing, our string for C in S. Okay. Let's call this current state. Okay. This current state is so it's started or something like that. So current state. Okay. So let's enumerate this. INC. Okay. If I equal to 0. Okay. And C. Uh, C, C is not in valid signs. Okay. If C is not in valid size, that means the first number is not valid size. And C is not in valid numbers. Okay. So just check quickly. Can it be starting with a decimal? The number with optional sign followed by one of the following digits followed by a dot, dot followed by digits. Okay. It can also be valid special. Okay. So special characters with the valid is only one. Okay. And C not in valid special. Okay. So if it is not one of this, it's going to be a lot of corner cases here. Okay. So that's why this is going to take time. So if I is 0, that means we are going to check the first thing. So first thing is 0th, and if C is not in the valid signs and C is not in the valid numbers and C is not in valid specials, okay, special characters, um, can it also be so if it is not any of this, this is true, then return false. That means it's not a valid number. Okay, that is to check the start. Okay, if I 0. Okay, so if I is 0, if we didn't return false, that means our first character check was true. First character was correct. That means we are done with the first character check. What about other things? Last. We don't know what is the last character, and we just update the last character as soon as we are done with this. The last character is C. Okay. Okay. If I go to 1, okay. If I go to the second, then second can be, okay. Second should be either a number, okay. It should not be a sign now, okay. So C is not in, C is not in the valid numbers. C is not in the valid numbers and C not in valid specials and C not in valid alphabets. Okay. Then I can return false here. So this is for second, but how long do I check like that? This is not just for second, this can be for anything. So if I is greater than 0, then I can check this. Okay. If I is greater than 0, then it has to be valid number. It has to be either a special character which is present in our list, or it has to be an alphabet, valid alphabet. Put that in the same sequence that we had. Okay. So finally, we are going to just return true. So to return true if this is happening. Okay. All right. So if I is greater than 0, then this is what is going to happen. And your last character is this. Okay. What else? You know that these are all invalid numbers. So if you have signs 2 times, it is also invalid. Okay. C is not invalid. C is not invalid. C is not invalid. Special. Okay. Now let's do one thing. Let's see. Uh, let's count the dots. Okay. If I have dots more than twice, that means it's a invalid already. So we can do that here at the top. So let's do one thing. Let's check counts here. Counter of S. You can just say counter S. It is going to give us the counts. Okay. Uh, if valid special in this, then we have to uh, check if it is more than twice. And valid, let's do this. The context. If this is valid special, right? Valid special is dot. If this is greater than 1, do a dot get here. Dot get is not present, and we'll have to do a dot get here. Dot get valid special 0. Greater than 1, return false. Okay, that's one more case. What else? If okay, what? Let's convert this S to a lower, okay, so that we don't have to worry about multiple S is equal to S dot lower. This is becoming a big E. Okay. If S valid alphabet greater than 1, then it's a valid number again. Okay. What else? It's a valid number if it is present 2 times without and all of that. These cases are okay, but we have to check more cases now. So this will pass a few test cases, but it won't pass the whole question. So it's only a dot, it's only a decimal. That means there are no numbers present. Okay, there are no numbers present. Then it has to be invalid. Uh, okay. Um, so start is correct, but it has to be followed by your than I thought actually. As length is always going to be less than 20. So if it is dot, that means it's a dot. Uh, that gives you, so if it's a dot, then just check this dot false. It will pass that case, but it won't pass other cases. Let's take this example that we have here. This is one case. Let's say It's going to fail the fifth one. This one, sorry. This is one E. Because this E has to be followed with a number. If it is not following a number, then okay. So if gonna false over there. Okay. Now let's check this. Okay. This false. This is invalid because you just want to relate it wrong. Cannot have E used to power a decimal value. What is saying? Followed an integer is followed by an optional exponent. A decimal is followed by an optional exponent. Defined by E or followed by an integer. E has to be followed by an integer. Okay. There cannot be E which does not follow an integer. Okay. So E should not follow decimal point. Decimal point should not be present after E. So let me check this. Last cat and um, exponent found. So let's say we have exponent found as false. As soon as we see a character, if C in valid alphabets, okay, exponent found is going to be true. Else if exponent found and true, valid special, then return a false check. Okay. After that, this is an invalid. This will also work. There's so many test cases in this, so that's why it's even after solving for this, I think it might fail for some of the. So that works. That works. What about this? This should work. Um, because we are already checking for invalid cases there. Cannot add more. Add it here. Anytime the character is not valid, then we just return it false. Okay. So it passes. Okay, so let's try. Dot followed by E, then one. Let's take this false because decimal number. The decimal number is defined by an optional followed by the following in digits, followed by dot, dot, followed by digits. Okay, so if there is a dot, then it should be followed by a digit, not by E. It is getting followed by an E. This is bad way of solving this actually, because we are taking one test case and trying to solve it. So can we think of rules that are given here and use these? Let's do one thing. Let's try to think of the rules and use that. Okay. So just comment this for some time. We can check that one more thing that we checked, which is just check this. If, um, then it's return false. That case should pass, but then it should be another case where it just keep on too many things to cover. Okay. So let's think. We covered a lot of them because we can see here out of 1500 cases, 1449 cases are covered. We just need to cover this maybe one case and it might get solved. Let's try that. Okay. Mm, all right. So it says if there are no numbers, then in that case, it is going to, it has to have numbers, right? So if uh, S does not contain numbers, right? Contains, so we need to have numbers in there. Let's just check. I will check. Present. Um, any case here for S dot is any not any, then return false. That means there are no numbers. There's not even a single number present. Let's do this test result. Plus and dot. Okay, let's try to submit and let's see how far we can go. Plus then E and then 3. This is again failing. Okay. So there are so many cases we might have missed here because the way we solved it is not the optimal way or the best way of solving this. Okay. After plus, the next element has to be okay. Let's do this. If last character, okay, is equal to last character is in, if last character is in valid signs, okay, and C It's not in valid numbers. Okay. Last character is with plus, minus, or if it's not a valid numbers, and C not in valid special, which is a dot, and return a false. Might solve the case. Okay. Here, valid sign. It's not in valid numbers. It's not in valid special. Return is false. Yeah, you see this? We added new case and then it suddenly dropped. Now we are not in passing growth mode. So, okay. Let's try to see this editorial, okay? Okay. So, all right, so we'll talk about something which is very hard and train. Approach one, which is follow the rules. Okay. The problem outlines a very specific set of rules. Let's pull all the possible characters into groups and then create a set of rules for each group. Then we can iterate through the input and evaluate if the characters are following the groups or not. Okay. Read through the problem statement very carefully. Very certain. Okay. One, digits means one of these. Okay. Both decimal numbers and integers must contain at least one digit. Okay, is that the rule? One check here. One of the following. An integer number is defined by followed by digits. Okay. Integer number is defined with an optional sign plus minus followed by digits. Okay. There is an integer number followed by optional exponent, and then there is an integer number which is followed with sign. Okay. Let's try to follow the rules that they're saying. Okay. Rules. Digit. First of all, there must all at least one digit in the input. So let's use a variable seen digit to indicate whether we have seen the digit yet. Signs. If the sign is present, it must be the first character in the decimal. Possible. Okay. Seen digit, seen an exponent, seen a dot. Everything is false. Okay. If C is a digit, then we say we have seen a digit. Okay. Else C has to be plus or minus. Okay. Uh, let's check this second approach once. Okay. Now let's view this approach from a different angle. There are three booleans variable and they can either be true or false. Each time we read a character in the string, we either stayed in the current state or we transitioned into a new state. So this is what finite state machine that determines if finite we're talking about. Uh, Design the machine picture of the directed graph. So this is what machine looks like. Okay. So this is your start. At your start, you are having three options. It can either be a digit, can be a sign, or it can be a dot. If it's a digit, then you go on to the first state, right? At this particular state, you have three options now. It can the next character. uh, I mean, that character itself can be a digit, or it can be an exponent, or it can be a dot. If it's an exponent, we go to this particular state. If it's a dot, we go to this state. What that finite state machine is going to look like. We are saying that these are all your one sinus system. We have to be designed. Um, all right, so let's do one thing. I think we'll have to skip this question because this question is taking first of all a lot of time. And by getting closer to the solution here by what we did here, but this does not seem like a way of solving. Let's skip this one. I'll try to address this one in next week. Just send it and say. All right, so this question is about given a reference of node connected undirected graph, do a deep copy. Each node in the graph, okay, we are given a graph and this graph is having value and the neighbors. And you want to create a copy of this. So this is your original, okay? Can't return the same graph, first of all. You can't, the nodes were cloned, but the graph is messed up, doesn't have the same, okay. So you want to create a copy of this graph here, right? So this graph is having values and then you have neighbors, okay. Going to create the copies. All right, let's take one more. So this is just one. Graph is basically like a tree, but you can have closed loops like this in a graph. There's a connection from 1 to 2. So 1 is neighbor of 2 and 2 is neighbor of 1. 1 has two neighbors here, 4 and 2. 2 has two neighbors, 3 and 1. All right. So graph can also be done by graph can also be traversed in a DFS or BFS manner. We'll talk about that in a bit. Okay. So we want to create a copy. Whenever you create a copy, we have to make sure that it is having all the nodes and the neighbors are constant, neighbors are same. Okay. So we solved a similar question where we created copy for the linked list. So I think we can do the same thing here. For that, we need old node and then we also need the mapping to the new node. Okay. We try to do that. So what we can do is, well, first of all, we go through the whole graph and keep a copy of what is the old node and what is the new node uh, that maps to that. Okay. Once we have that information, we can then again go through the graph, old graph, and uh, this time we can update that new graph with all the neighbors using the old graph. Okay. Let me just think. Is that the only way, or is there any better way of doing this? So I take one and I create a clone of this one. So store it in the hash map. I go to 2, I take a clone of 2, store it in the hash map. I go to 4, take a clone of 4, store it in the hash map. 3, take a clone of 3 and store it in the hash map. Okay. Next, I go to 1. I know what it is clone. I know what are the neighbors of 1, and I also have the clones of the neighbors too. Okay. So I can create that clone and I can just update that graph properly. Okay. So that's one way. Let me just think if there's another better way. So let's say you start from here, you create a clone of 1. Okay. After that, you go to the neighbors of 4, neighbors of 1, which is 4 and 2. You check 4 and 2 has two neighbors. one has two neighbors, 4 and 2. You create clones for 4 and you also create clone for 2. All right. And okay. Then whatever the neighbors of 4 are, 3 and 1. So 1 is already present. We create a clone for 3 and store it. Okay. Can we just do it in one pass? Anytime a node is new, we can create a clone of that and store it in the hash map. If the node is not new, then we can just use the old node that is present in the hash map and use it. Okay, so I think we can do that. So that way we are going to pass through this particular tree is a BFS or DFS. We can do both. This graph, we'll do a BFS. So for BFS, we need queue, we need visited and all of that. Because this is graph, we need a visited set so that we don't visit the same node twice, or else you'll be in the infinite loop. You'll never get out of that loop. Okay? So we need a queue, which is the queue here. We need visited set, okay? Because this is a graph. Queue dot append. First thing that we do is we just append the node, okay? Starting node.
Sir, can you please repeat questions? Questions, sir?
Oh, I didn't send the question. Okay,
Yeah.
that's the question. All right. So we start from one, and then we check old to new map. This is the old to new map. Let's do this. While queue is not empty, so we want to get the node from the queue. Node is equal to queue dot pop left. You got the node, and you got the node. You add the node to the visited. As soon as you append to the queue, add it to the visited. Okay. So visited dot append the node. So visited dot add. As soon as you append to the queue, you should add it to the visited because you have visited that particular node. Okay. All right. Now let's go through the neighbors. Neighbors of node dot neighbors. Okay. Node dot neighbors. If neighbors not in visited. Okay. If the neighbors are not in visited, first we'll write the BFS and then after that we'll write the whole thing, the remaining things. So if neighbor is not in visited, then visited dot add neighbor, and then also queue dot uh, append basically your neighbor. So you're adding the neighbor to the queue, and then you're popping left until unless your queue becomes empty. So this is your BFS for the queue. Okay. What you want to return? You want to return another node. You want to return new node or head of the new node, right? So let's just check. Let's go. You want to return a node here. Okay. So we have a node that we want to return. All right. Now let's create this map. Okay. So anytime we pop a new item, we create a copy of this. So the way we create the copy is by using this node object. This node object is going to have node.val as the copy. And we have neighbors also. Neighbors we can keep empty and then we can append them later. Okay. So for now, neighbors are empty. Okay. So let's just call this new neighbors, or new node neighbors. The new node neighbors are empty for now, and this is what we want. Okay. Uh, this is your new node, and we want to put it into the hash map. The hash map of old node is equal to new node. So hash map of your old node is this, points to a new node, which is that value. All right. After that, whenever we find a neighbor, If the neighbor is not present, uh, yeah, then also create copies of your neighbors now. Okay, let's create copies of your neighbors. Give me a second. Let me start. So let's create copies of your neighbors. Do I need to create copies of the neighbors or just append? So because I want to append them here, I need the copies of neighbors too. Okay. All right. So let's do this. So let's create copies of neighbors also. Let's create copies of the neighbors. Your neighbors copy is getting created here. Your neighbor is copy is going to get created. Create the copy inside this particular thing. Just create for all the ones. Create the copy inside here. All right. Let's just think. Uh, so I go to one. I cop one. Then I create a copy of one. So copy of one is going to get added to this old to new map. So that is getting added here currently. After that, I am going to iterate to the neighbors of one, which is 2 and 4. So I'll create a copy of 2. Let's create a copy of 2. If any I not in, if the copy is not already created, only then right? If any I not in this, then let's add it. Okay, and I is equal to node neighbor dot val. Okay? And what should the neighbors of this be? Neighbors of this is going to have your first thing, it is going to have your node. Okay, that's for sure, because we know that the node is the neighbor of it. It is we are coming from there, so that's why node is going to be the neighbor of it. All right. So this is going to add a copy of 2 into there. Not node new. So actually, copy of this new one. It not be pointing to the old one at all. So this is what we have. Okay, and okay, the new node that we have dot neighbors. We want to append dot neighbors dot append neighbors here. Correct. So you want to append the neighbors as soon as you find a new neighbor. All right, that sounds okay. Let me make this part. So let's try to handle this. So we got to one. One got popped out here. New node neighbors is empty for now because we don't have any neighbors there. Uh, it's empty for now. So when I start out, I can say my new nodes does not have any neighbors for now. So this is my new node. Okay, this is my new node. Do I have to check if it's present? Okay, let's just call it new node. Okay, new node is equal to dot get is present. If it is not present, then create a new node. That's my new node. Right? If it is not present, create a new node and add it to your node here like this. Okay. If it is present, Just make it simpler. So this is what we have. If it is present, then get the new node directly. If it is not present, then create a new node. So this is going to have a new node for the current node. Okay. After that, if the neighbor is present here, then you just create a new one if it is not present, and you add node already as a neighbor to that. Then append neighbors. This neighbors here. Let's try this. That's error. Okay. None type has no value. What's the none type here? Some empty. Node. So we got somewhere, but our neighbors are getting duplicated. Neighbors are getting duplicated because we are initializing them with this threshold. Yeah, so initializing that way. You don't need to initialize that. All right. So the logic was the straightforward logic that we discussed, which is we have a map, and this map is going to keep track of the old and new, similar to what we did in the linked list. Uh, if the node is not present, then we create a node, right? Uh, Actually, this line that we have, this also can be written the way we have this written. So let's do that. It's new. Neighbor. Neighbor is equal to old node dot get. Get what? Get your neighbor. It's not present, then get a the neighbor value here. Okay, this is what we want. Is there any case that we have missed? Let's just think about it. So if it is empty, we just return it. Uh, are updating this so that we can return the no head properly later. We have to send the latest one, which is okay. The new one is present in this map. What else? Let's hand run this. So we take one, we pop one, then create node for one. After that, we go to the one's neighbors. Then check if one's neighbors were created. If they're not created, then we create nodes, a copy node for that, and then add them as neighbors to the new node that we have. Okay. If they are not visited, then add them to the visited and also to the queue so that you can visit them. So when you go to 2, now you are going to visit 2 uh, because you're popping left, right? So first item that gets inserted is, let's say, 2. You pop left, you go to 2, you check if 2 is present. 2 is present in this case because we created when we were visiting from 1. So we got to 2, 2 is present. We take 2 here, okay? What are the value of 2 or the new node is, and then we are going to append neighbors of 2. So 2 is having 2 neighbors, which is 1 and 3. 1's node is already created, so that will not get created, but 3's node is going to get created, and it gets added here. Okay. Looks like this would work. There you go. This works. Okay. Uh, let's just quickly check the editorial. BFS, the BFS, BFS code. It's not a node, then just clone graph. Okay, so clone graph is a query is all that they're trying to solve. This node is not in the visitor, then return self. Keep on calling the clone graph because this is DFS. Pop left, they did the same thing. What else? Is there anything that they did better than us? So kept track of visitor and its respective clone. Okay. So this visited itself can keep track of whether it was visited and their clone directly. So we don't need this map. Okay. Visitor is also doing the same thing. That's what they do. So whenever you add it to the visited, just create a clone, create a new thing for the visited. Okay. So that visited can be used as your map directly because it can be used as a dictionary. Time complexity is O of m plus m, where m is the number of edges, n is the total number of vertices. Okay. Space complexity O of n. All right. Let's continue. So time complexity of this is O of n plus m, m being total number of edges, and edges because we have neighbors here like this. So, and n being total number of nodes. We are going to visit each node at least once. We are going to visit each node only once, not at least. Let's move on to the next question. The question says we want to write a least recently used cache. Initialize the LRU cache with positive size capacity. Whenever you initialize, you know the capacity of your LRU. Int get returns the value of the key if exist, otherwise -1. Okay. Put is going to put it in the cache. Update the value of key if the key exists, otherwise add key value pair to the cache. If key exceeds capacity for this operation, evict the least recently used key. So least recently used key code, we want to evict it. So that's how your cache basically works, or least recently used cache basically works. So if you have keys which were not accessed recently, then remove them because they are just taking unnecessary space in your cache. And to make cache faster, you can just remove them. So your get and put function must run in O of 1, which is the requirement. So your when you do a get, it should run fast. When you do a put, it should just do it in one go. Okay. So how can we do this? So cache that you have here is basically we need a queue which is first in, first out. Anything that is inserted to the queue first will be removed from the queues first. Okay. Um, we know that the capacity of queue has to be equal to the length of the queue has to be equal to the capacity of the queue. So let's create the capacity here. Self dot capa is your capacity that was set. Just take this example which is given to us. So what we are doing is first we are initializing a capacity of 2. So 2 is the capacity of the array. After that we are putting 1. This put function takes key and the value both. Okay. So 1 is inserted and its value is 1. Okay. 1 is the key that is getting inserted. We can keep only keys in the cache. Okay. In the queue because keys are going to get evicted. The values have nothing to do there. Okay. Self dot let's say we say our keys, it's going to be of capacity. Start off with what are the key values? Key is going to be positive. Right? So let's just put the capacity of -1 into capacity. So we want to have this many number of items in your queue, or we can just initialize to D queue. Okay, that's what W queue have. Okay, all right. Now let's talk about putting things into the queue. So when you get a new value, you want to put it into a key value pair. Okay. Um, so your key value pair, you need to maintain the key value pair also, right? So dot cache is basically your dictionary. When you put it, you want to put it. So first insert it. First insert it to the queue. Dot append that value to the queue. So you append it at the end. The key got appended here. Okay. If length of this particular thing is length of keys queue is greater than capacity, then you want to remove one. So you just want to pop dot pop left. So one got removed. What you want to return here is basically your cache. You want to return anything here? None, right? So you don't have to return anything. Then your cache key that you just now inserted is basically your value that you have. Okay, the value that you inserted. When you get, all you have to do is just check if it is present in cache and then return it. If not, then return -1. Okay, return uh, dot get what are the keys that you have, comma -1 if the key is not present. Let's check. This is what we have written now. We have a capacity, which is the maximum length of your cache, your keys in your queue, and then your cache, which basically holds the key value pair. When you put something, so let's say you put 1, the value of 1 is 1. So your cache became 1, 1. That's your cache. And your queue became 1. Okay. After that, you inserted 2. So then you inserted 2, 2, and the value of 2 is also 2. So this is going to get pushed in the front. 2 is getting appended here. After that, you try to get it. So when you try to get it, okay. So when you try to get it, going to get the value, and that value, because it is getting, it is recently used now. So you have to insert it back. Okay. So this is my answer, right? If answer is not equal to -1, okay, that's what you're saying, right? So values is not present, return -1. If it's not -1, then I have to put it back again. So I have to say self dot put. What do you have to put? I have to put the key and the answer back in. Okay, so that it gets moved to the top of the list again. So I did 1 comma 2, so that means this 1 is going to get moved to the front here now. After that, 3 comma 3 is added, so this is 3 comma 3 is added, and 3 is getting pushed here. After that, 4 comma 4 is getting added, so let's add 4 comma 4. So 4 comma 4 is added. As soon as you add 4 and 4 comma 4, the capacity became actually the capacity became more than 3 here directly. So this was evicted already. This was evicted. If that is evicted, then water was popped. We need to delete that from your cache also. Okay. So this is your pop key. Then delete it from your cache also. Delete your pop key from the cache. You have to delete the pop key from the cache as well. Put the value. That looks fine to me now. So when you get, you put it back into the value so that it moves ahead of the queue. Okay. When it tries to just move it ahead of the queue, then there's nothing. Okay. See, first question itself is wrong. Why? Because we're not returning the answer. All right. So return looks about right to me. Let's try to submit this. Yeah, right. How come we have a key error here? Key error because we have cache which is getting added, which is correct. Get the value. What is the, we put 2 and 1 in there. 2 and 1 got inserted. Just check this. 2 and 1 got inserted. After that, this is your, oh, the keys collide. Okay, okay. Um, so what is happening is next time we're putting 2 comma 2, right? So your 2 comma 2 is getting put, but the 2 comma 2 in the cache is getting replaced like this, right? And your capacity is 2 here like this. Okay. Next time you're inserting 1. So 1 is getting inserted. And because this is 1, this one got removed. And because that got removed, we are deleting it from the cache also. And next time the 2 is getting removed again, it is not able to find it because we removed the 2. Okay. So we have to make sure when the duplicate key comes, what to do. When you want to replace the values in the queue. Okay. Do this. Okay. Do this. All right. So if key in key is already present in cache, okay, so if key is already present in cache, then we have to move it to the top of the queue. That is for sure. But we also have to remove it from the middle of the queue somehow. Okay. How do we do that? So our data structures are wrong here. We have a queue, cache. Can we update this cache to something like this so that the cache has the key, it has value, then it also has how recently this was used, correct? But if I do that, then I'll have to update the whole cache every time I insert something. Okay, what I can do, more thing is mm, I can keep the key and I also can keep uh, when you have distinct values, but we have to make sure that we do get and put any O of 1. Okay, let's focus. Okay, so what do we have here? So we have a case where you have duplicate keys getting inserted. In that case, what to do? In that case, if the key is duplicate, then don't spend spending is important because without that, how would you move to the first? Uh, this is kind of- you need the queue because that is how you evict the least recently used. Okay, what we can do is if key is in your cache, the key is in cache, then we should only update the value. Sorry, if key is not in the cache, then we should do that. If key is in cache, then first thing we have to do is we have to make sure that it goes to the top of your queue. Uh, how do we move it to the top of the queue? Because we don't know the index at which it is right now. Correct. Even if we know the index, we will have to move everything. We have to create linked list here because deleting from linked list would be, but how do I go to that spot in the link list? So I have a cache. The cache is going to be key and the value. Can I store something else with that? Key value and its location in the queue. Would that help? We can store the key and the value and the location in the queue. Then I can use that value somehow. Location in the queue. What do I do with that location in the queue? I can delete that particular item, but yeah, that won't solve it. Deletion is going to be O of n. It is deleting from somewhere in the middle. Can we use this dequeue somehow? Um, we do left first, then append. That also is fine. Delete from the cache is fine. Um, we'll have to check the solution. Let's check the editorial here. Let's start by thinking about how to implement data without carrying out the time. Doubly linked is what we have here. We want to create this. Want us to create more data structures. So we think of that. This order dictionary is there, but I don't want to use order dictionary. That is, okay, let's think. Let's use the order dictionary for now. So order dictionary has this function which is move to end, which will move it to the end. Item. What is this false? Okay, let's try to do that. Remove the capacity. Let's create a order dictionary. Self dot let's call it cache. Right. This is your order dictionary. If you want to get it, then you get it directly, or else it just return it. Answer is not equal to one. You have to put it into the self dot cache. You want to put it on the top. So move to the end. Move to the end. Your answer. While putting first thing we check if it is present in the dictionary and caching. Self dot caching. If it's in the cache, then move it to the front. The way we did it. Or you can just call put also. That's fine. Move to the end, and then we just update the value. So whatever the new value is. If length of cache greater than self dot capacity, if greater than capacity, going to pop self dot pop item. You want to pop the first item. That's why there is a false here. This works. We have this new order dictionary. This order dictionary has moved to end, and this pop item, if you say false, then it is pop. It is going to pop the first item in your order dictionary. Concepts are important here. Move to end. Um, let's check any solutions if there are. We created a map here. Which is a dictionary. If key is not in map, then return. Key with the value. Delete the key. And again the value. Return the value. Okay. Delete the first item. He's assuming that keys are instead of doing this order dictionary, he's assuming that the keys are ordered. So just delete the old one and remove, add the new one. That's all. Basically doing the same thing. Any other solutions? Let's just click these. How do we solve this with doubly linked list? So what they're saying is you can have a doubly linked list, and that doubly linked list basically keeps track of your uh, key and values. This is your doubly linked list, which is having your key and which also has your value, and it has what is your next and what is your previous. Right? The steps is you want to store something, then the way we store it is create a new node and that new node is going to have the key and it's going to have the value, and its next is going to point to none. Its previous is going to basically point to the latest node that we have in the cache. Okay. We need a dummy node. Have key value, doesn't matter. We should initialize. That is we go tables. Then make it a circular list. Adding later on this one to spend more time. You're given a let's solve this one. We're given an integer num. We can swap two digits at most to get the maximum valued number. Return the maximum valued number you can get. Okay. So you're given this swap 2 with 7 and you get the maximum number. All right. So how to swap the numbers here, right? So 2, 7, 3, 6. Okay. Swap 2 with 7 and you get the maximum number. Swap, no swaps required because this is already a maximum number. Okay. And at most once, only one swap is required. So you cannot swap more than once. So this is your number. You have to find out what needs to be swapped. Okay. So what we can do is we can check what is the largest number from the right side. The largest number is 7. Okay. And we can check from the left side, from the right side, what is the smallest number. The smallest number is 2. Okay. If your largest number index is greater than your smallest number index, you can swap them together and you get a number. Okay, let's test that hypothesis. You have 9937. Okay. If this is your number, then what we can do is first check what is the largest, smallest number from here. So the smallest number is 3. Okay. After that, from right side, get the largest number, but only go till 3. Okay. Only go till 3 because you want to swap it with 3, right? Only go till 3. All right. So let's check that. If I only go till 3, then my largest is 7. I can swap that. I can get the number. What about 9, 4, 3, 7? Okay. Smallest number is 3. Largest number is 7. This 4 and 7 needs to get swapped here in this case. Okay. So the logic that we discussed, that won't work here. All right. So what else can we do? 4 and 7 needs to be. What about this? So you start from here and check what is the largest number on the right side. Okay. 3 has the largest number of 7 on the right side. Okay. Here, largest number on the right side, 4. The largest number on the right side is 7. And we can swap those two numbers. 2, 7, 3, 6. All right. So we start with from 2. What is the largest number on the right side? The largest number on the right side is 7. And then we can swap those two numbers to get the highest number. 3, 7. What is the largest number on the right side? This itself is largest number. This itself is largest number. Uh, Largest number for this is 7. Largest number for this is nothing. So this and this can be um, swapped to get the maximum number. Let's try that might work. Let's check one more. 1 7 1 1 7 9. The largest number on the right side is 9. So we just move 9 to the first here. And we can make the largest number. Correct? That would work. Yeah. So let's create a list which is largest on right. Okay. So we'll initialize it to be -1, because if there's nothing on the largest, if that itself is the largest number, then it's not going to have anything. That to be it's one there. After that, we have to go through the number one by one to check the largest on the right side. So we need largest, or we can just say call it current largest. Current largest. Current largest is, let's say, math dot infinite number, the smallest number that we know. We need to iterate through this num in a reverse direction because we want to get largest on the right side. Okay. So for I in range, first of all, you have to convert that into a string, and then you have to go in the reverse direction. We need the indexes. Yeah, let's just we have length of your numbers -1, -1. Okay, the current largest basically uh, equal to max of what are the current largest is comma and the num I. Okay, so you update your largest number. So your current largest number is updated now. What we are saying is you start from here. Current largest for this is 9 itself. If uh, current largest is greater than my current number, okay. Current largest is, we have to convert this to a string number first. Let's just convert this to a string. So that is what the number is. Uh, String num I. Okay. So if your current largest is greater than, right now, sorry, I'm just somehow. This is 1179. Okay. So we start with 9. All right. We check 9. There's nothing largest to 9 on the right side. So 9 itself is the largest number till now. If current largest is greater than, which is not true, so we don't do anything. Okay. And then we update your current largest to be uh, what are the current numbers. So this is S current num. Okay. Let's convert this into data. Current largest. If my current largest is greater than the num, then I need to know what is the index of that current largest. Okay, just call this current largest index. We need the index. A second. All right, so we need the index. So this is correct. So current largest index is fine. We don't have to start from -1, but we can start from -2 because current largest number index is basically the last number that you have. The last number you have is length of your s num -1. This is your current largest number for now. Whatever is, so this is my current largest number to start off with. Okay, and that is the index of the current largest number. So what I want to do is I want to check this number here like this. So if this, okay, current largest index, if this number is greater than the number that I'm seeing right now, that means I want to update the index here. So my index has to be updated. This has to become whatever my current largest number index is. Okay. All right. That's fine. My yeah, if my current largest number, okay, if my current largest number is less than or equal to this number itself. Okay, if it is less than or equal to this number itself, then I want to update my index of the current largest number to the number that I saw. The current largest index is equal to I. Okay, so my current largest index becomes I here. Check if this is checking out properly. So I have this string, and then I have this list which is starting with -1. All the numbers are assigned with the length. Current largest is basically this number. When I start out, it is not going to have any index. After that, I go to 7 because I'm going in the reverse direction and I'm skipping the first last item. So I go to 7 and I check 7 is 7 greater than something. Yeah. 7 uh, if my current largest index, which is this, is greater than my current number, which is true, that means largest on the right for 7 is basically ninth. Okay, that's fine. After that, I will check if my number itself, which I'm passing right now, if it is greater than or equal to my this current index, I have to current largest, make my current number as the current largest. Okay, this looks fine. All right, so this is how you get the list of current largest on the right. So this is going to have current largest of the night, right? So these are the indexes, right? 0, 1, 2. These are the indexes. So the largest on the right is basically going to have 3. This will be 3 again. This will be 3, and this will be -1. Okay. Now what we want to do is we want to start parsing from the right side here. Okay, and we can just check that this can be swapped with this. Okay, because this is not -1. Okay, so we can just swap these two numbers and we can get our answer. Okay, so let's do that. For I in largest on the right. Okay, so those are the indexes. Largest on right, call it index. Okay, if largest on the right is not equal to -1. Okay, if it is not equal to -1, then I have to update this. So update What am I checking right now? So, so let's just go through the list. Okay, I in range length of s comma num. So we go one by one. Okay, if largest on the right I is not equal to -1. It's not equal to -1. That means I need to do a swapping here. Swap is s num I and s num with the largest number on the right I. Okay, is equal to swapping. That is swap. And you done. You return integer which is your s num. Else return num as is. Okay, let's try to run this. Assignment won't work for the strings, so we have to convert that into a list and then return it like this. That worked. Doesn't work here. So output came 9193, but the answer is 9913. So our number is 19913. So you start from the, okay, let's check this number. 199. So the largest on the right is -1, largest on the right is -1, largest on the right is -1, largest on the right for this is largest on the right is equal, largest on the right is itself, largest on the right is itself. Then largest on the right for this is 1, for this is 1. We are swapping this, but we should be swapping this. That's because we are checking this condition. So if it is equal to, don't update. Only if it is less, then update it. This is test case. If it is equal to, don't update it because we want this to be, it's also to be true. So, but I would say very fast. Anyways, so that doesn't matter. Mm, the mistake was we have to update it properly. Let's see if we can do one more. Okay, so the question says we are given a list of accounts where each element is a list of strings where first element is name and the second is emails. So you have accounts here and each account is going to have name and the emails, name and the emails, name and the emails. Okay, we have to Now we would like to merge these accounts. Two accounts definitely belong to same person if there is some common email in both the accounts. Note that even if two accounts have same name, they may belong to different people, as they have, a person can have many number of accounts, but all of their accounts definitely have same name. A person can have any number of accounts initially, but all of their accounts definitely have same name. Okay. Note that even if two accounts have same name, they may belong to different people. That's fine. Two accounts definitely belong to same person if there is some common email. Okay. All right. So we want to merge these accounts together so that we can have John and all of his emails in front of him. Mary, all of the emails in front of her. John, all of the emails that belong to John. Okay. So we see this John and then we see this John. Okay. This John and this John have both common email. That means this person and this person are same. So you merge these two together. This is not common with anyone, so you do nothing to merge there. Okay. All right. So what can we do now? So we are having emails like this. And emails are basically deciding whether that person belongs. Okay. Um, we have emails here. Okay. So what we can do is check this email. This email. These two are connected basically because they both belong to same person. After that, I check this person, this, and then I see uh, already present. So this can be joined back into the dictionary. So what we can do is we have all of these emails, right? So all of these emails uh, can become keys of a dictionary. Okay, so this is a key, and the value is basically all the other emails which are common to this. So, for example, this John Smith is part of John, and then these are the email IDs which are present for that same person, four email IDs. So, this John Smith will have four items in that dictionary as the value for that John Smith. Okay. Uh, all right. So the emails will have four values. When do I create the keys in the dictionary? So the dictionary keys will be created anytime I see. Okay. What else can be thought here? We have this. Just think. We have this. Key value. So we can and the values being your emails. Okay. Mm, Name and the email being the key, and then all the emails which are related to this being that. Okay. After that, what we can do is we can have a set which is visited. That means we have already found uh, connection to that, or more accounts for that particular person, and this visited should have uh, the emails that we have visited. Okay. All right. Yeah, let's do that. So let's put all the visited emails in the emails. So what we can do is we can go through these accounts, and if this name comma email is not present, we can create a key value pair. where the value is going to be list of all the emails, including this email also. Okay, and then after that we can iterate through this particular dictionary and go through all the keys first, and then anytime we encounter an email, add it to the visited and build our answer basically using that name and the uh, emails. Okay, I think there's something that, and your answer is basically, what would our answer be? Um Answer has to be a list of lists, that's for sure. But how am I going to create this list? When I'm iterating over this particular dictionary, this dictionary is going to give me name, which is fine. It's going to give me email too. Okay. What use is that? So do I need name there, or can I just keep name here and just keep emails here like this? So if I do that, I can get names directly from that, and then this email is connected to all the emails that is present here. If it is first time seen, then I add it there. It's already visited and already visited. John Smith. So what we can do here is your John Smith is going to be your key, and then values are going to be John Smith itself, John New York itself, and then emails also have to be sorted this way, but okay. John Smith is there, John Smith is going to be there, and then you have John 00, the email, which can be a set here. It can be a set actually. So you have key, and your values are basically your name and a set of all the dictionaries that you have, all the emails that are present for that. Okay. Um, so when I iterate this, I create a key value pair. My key is my email, and the value is my name, and then all of these emails that are due. After that, I go here. Let's say I encounter this. Now, because I've encountered this, uh, I will create another email there, and then I'll say visited node as node name as John, and then its email is going to have these two as their emails in the values. Okay, that's create now. So those will have John 00 and then John Smith. Emails present there. Right. Okay, so John. One thing we can do is we can create a connected graph here for John. John is connected to John New York, and John Smith is also connected to John 00. Then vice versa. John New York is connected to John Smith, and John 00 is connected to John Smith. Uh, okay. If I create that graph, then I can just iterate over that graph and get my answer. Can we do that? Just think. So John Smith, John New York. We can create John Smith here, and then John Smith can be connected to John New York. John 00. Three can be connected to each other. They'll form a closed graph here. After that, we go to Bravo, its own graph. Okay. All right. So what we can do is we can take this as your key. All right. Key value pairs need to have. So you have your name and your email, and the values are basically going to be same thing, name and your email. Okay. And then name and your email one. What are emails that you have? Email one here. So this is basically your email, which is connected. It is not connected to itself. You don't need this. It is connected to the next email that we have here. Okay. After that, you go here. You see that this is present here, and it is already present in the. So we can check the emails that you have and append it here. Whatever the name is, the email too got appended there. All right. Next, we go to Mary. Mary has different name, different email, and then she will get added. Okay. Yeah, we can actually use this way of keeping things. So once you have this, you go through this particular list or this particular dictionary, and then keep track of whether you have visited it or not. If you have visited it, don't visit it again. Okay, let's build this first. Okay. So let's build that. So for us to build that in for the in accounts, okay, A0 is your name or for email, one all of the other values. Okay, then let's build stationery, right? So this is our, let's call this stationery or length and emails. Here like this. Dictionary of names and emails. If name, comma, email, not in dictionary of name, then dictionary of name, comma, email equal to an empty list. Okay, and then you can just take this value and append it. Else dot append. You can append the same value also, saying that it is connected to itself, just to keep it simple. So append same thing. Let's just append this. All right. So we have this dictionary now. This dictionary is basically going to have name and emails the way we want it. Name and their emails, name and their emails, and it's already present. It's just going to append it. Okay. Now let's go over the dictionary and keep visited track. Keep track of the visited here. Fill the answer in such a way that uh, build the answer here. Okay, let's go through this first. So for dictionary of dot items, so we need name and we get an email. We get name and email. Email names, not yet email. We get name, email. That's one. And then we get just to keep it. So let's just get the items first, name and email, and then call it connected. What we have. Okay. All right. We want to iterate through this whole thing. Connected name, connected email in connected name and connected emails in that. Um, if this not in what we want, visited, then visit them, add them to the visit. Okay, and your answer is basically going to be uh, your answer going to be build answer, right? So you got the thing that you want. Using that, you want to build the answer. So let's just print this once. This is what we got John Smith connected with John Smith itself, then again connected with John Smith, then connected with John New York. So this is my key and it is connected to this value. After that, my is this New York and it is connected to John New York, John 00, just John New York. Then I means that it's not it's connected with this connected to John 00. How do I merge all of this together? So John Smith, when I go and check, John Smith is connected to John New York. So stuck. Let's check the answer. So what they're saying, create a graph, then visit that graph. So everything is this. Right, that's it. Okay. And if we just create a graph, we don't have to worry about this stuff. Do a BFS or DFS, both are going to be the same thing. Uh, Graph here. Okay, let's try to create a graph here. Okay. So we need a graph. So let's create a class of graph. Class graph node. Okay. We need a class graph node. Let's define something. Define. What do we need? Node itself, or the value of the node, which is your email in this case. With name of that email, and you need neighbors. These are three things that you might need in the graph. Self dot value. Let's just call it email. Self dot name. Self dot. I'll just call it any ad. Let's call it the whole thing. Neighbors is equal to neighbors that you have here. This is your graph node. All right. Now let's do one thing. Let's build the graph by going through the list that we have here. How do we build the graph? So for building the graph, first go to the value and then check for connectivity. Yeah. We need node objects. Okay. We need node on the objects. So graph node objects. Keep it empty for now. Then we are iterating. So for account in accounts, we'll iterate over the accounts and we'll take the name out. Name is account 0th position for email in account 1 colon. Okay. Then we get the graph nodes here like this. If uh, name comma email not in graph node objects, then we have to create a new node for this. So let's just create a new node for so our new node is equal to uh, graph node, and this graph node requires name, right? Requires email first, then the name, and then it requires an empty neighbors to start off with. Uh, okay. What else? It is not present in there. If it is present, These two are okay. If it is present, then bring it out. Okay, then bring out the name and email and neighbors. Dot append the neighbors to this. For my neighbors that I want to append, um, all right, guys. I think I have to stop today. My head is already spinning. I'm not sure what's happening. Sorry about that. We'll continue tomorrow. Somehow my head is not working today.
Okay, sir. Thank you.